Welcome back to the podcast, folks. Today we're diving into the incredible world of atomic structure and the quirky properties that make each element unique.
That's a fascinating topic. Right, so the idea here is that the diverse chemical behaviors we observe really stem from the internal structure of atoms, correct?
Absolutely, exactly. It all starts way back in time, long before modern experiments, when early Indian and Greek philosophers speculated that matter was made of these indivisible particles, which they called atoms.
That. And then, fast forwarding to Dalton's atomic theory in the early 19th century, atoms became the building blocks, right?
Indeed, yes. Dalton's ideas were super groundbreaking. They explained the law of conservation of mass and the idea of constant composition. But things really got interesting when experiments showed that atoms weren't actually indivisible.
Yeah, like when they started finding out about electrons, protons, and neutrons?
Exactly. With experiments using cathode ray tubes, scientists like Michael Faraday and later J.J. Thomson discovered electrons, the negatively charged particles that make up part of every atom.
And Thomson even measured that charge to mass ratio using clever setups with electric and magnetic fields.
Yep. Thomson's work, with his famous plum pudding model, think of it like a watermelon with seeds scattered throughout, was one of the first attempts to explain how electrons fit into the atom.
Though today we know it's not quite how it works. Definitely not. And then came Rutherford, who totally flipped the script with his gold foil experiment, showing that most of the atom is empty space and that most of the mass, along with the positive charge, is concentrated in a tiny nucleus.
Right. It's almost like comparing a ping pong ball inside a football stadium. Tiny yet immensely influential. Yeah, exactly. It was a real aha moment. But even Rutherford's nuclear model wasn't the final word, as it couldn't explain why the electrons didn't just spiral into the nucleus, given the classical electromagnetic theory.
That's the crux of the problem. If electrons were on classical orbits like planets, they'd keep radiating energy and eventually crash.
Precisely. And that's where Bohr steps in with his quantized orbits. His model showed that electrons can only exist in certain allowed energy levels or stationary states, and they only emit or absorb energy when they jump between these discrete levels.
It's almost like stepping on a staircase. You can't stand between steps.
Exactly. It's like a staircase that offers only fixed positions, which explain the hydrogen line spectra beautifully.
And the entire Balmer series comes from those transitions, right? Right you are. The hydrogen spectrum, with its series of bright lines observed when hydrogen gas is excited, directly demonstrated this quantization.
Absolutely. Each line corresponding to a specific jump in energy levels. And speaking of energy levels, let's not forget how electromagnetic radiation fits in. On one hand, you have the wave theory, which, as Maxwell and Hertz showed, describes light as oscillating electric and magnetic fields.
Electromagnetic waves travel through the vacuum at the speed of light, about 3x 10 to 8 meters per second, right?
Yes, that's it. But then, experiments like the photoelectric effect threw a curveball to classical physics.
Right, because even faint light could eject electrons if the frequency was above a certain threshold.
Exactly. And Albert Einstein, building on Planck's quantum ideas, explained that by proposing that light is made up of discrete packets, photons.
Oh, absolutely. And he showed that the kinetic energy of the ejected electrons depends on the frequency of the light, not the intensity.
Yes, and that was a pivotal moment, confirming that light has both particle and wave characteristics. Quite a revolutionary idea.
Totally. It's that duality that set the stage for quantum mechanics.
Now, when you talk about electrons behaving like waves, it gets really intriguing with de Broglie's hypothesis. He suggested that particles such as electrons have wavelengths too, which we can actually measure using diffraction experiments.
And that's the idea that led to electron microscopes, enabling us to see at scales we once thought impossible.
Right you are. And then comes Heisenberg, who told us we can't know an electron's exact position and momentum simultaneously.
That uncertainty principle really shifted our understanding of the microscopic world.
It sure did. Imagine trying to predict exactly where a moving car is, and how fast it's going at the exact same moment. If you hammer down on one measurement, the other becomes fuzzier.
Yeah, though I often wonder, isn't that just everyday life? Sometimes, details blur when you're in a rush.
Laughs. True enough. But in quantum terms, it's a fundamental limit imposed by nature itself. And that's why modern chemistry and physics depend on probabilistic models to describe electron behavior around the nucleus.
Indeed, the cloud model or orbital theory takes over, which is a far cry from neat circular orbits.
Absolutely. And speaking of orbits, Bohr's model, while useful for hydrogen, falls short when handling more complex atoms where electron-electron repulsion and additional orbitals come into play.
That's when we really need to hand over the baton to quantum mechanics.
Right. In more advanced models, electrons are described by orbitals, regions in space where you're likely to find an electron, and these orbitals are defined by quantum numbers, which, believe it or not, come from solving Schrödinger's equation.
Yeah, and that equation is at the heart of modern quantum theory, determining the probability distribution of electrons.
Now, something I find absolutely interesting is how these quantum mechanical models tie into spectroscopy. The line spectra of elements essentially serve as unique fingerprints.
Like how we identify stars or even discover new elements. Helium, for instance, was first detected in the sun's spectrum.
Exactly. And those discrete lines come from electrons transitioning between their quantized energy states. The energy differences match up perfectly with the wavelengths or frequencies of the light being absorbed or emitted.
Right, and that's brilliantly captured by the Rydberg formula, which nails the pattern for hydrogen spectral lines.
Yes. And while Bohr's model set the stage with its success in explaining hydrogen's spectrum, it couldn't account for more complex phenomena like fine structure, hyperfine splitting, or the Zeeman and Stark effects.
That's a good point. Bohr's model was revolutionary but had its limitations, sort of like an early draft before the full, intricate quantum picture was painted.
Right. And it really is amazing how each step of discovery forced scientists, compelled us, to refine our understanding further. From Dalton's simple atoms to the modern quantum mechanical model, it's been quite a journey.
Absolutely. It's a testament to how science evolves over time.
Now, let's address some experiments that really cemented these ideas. For instance, Millikan's oil drop experiment not only determined the charge of the electron, but also underscored that charge is quantized.
Yeah, that experiment was pure genius. Observing tiny oil droplets and concluding that charge can come only in multiples of a fundamental unit.
And then we had experiments on electromagnetic radiation and blackbody spectra that pushed us to think differently about energy emission and absorption.
Right, because the classical model couldn't explain why hotter bodies didn't just emit infinite amounts of energy.
Correct. Planck's quantum hypothesis, where energy is emitted in discrete packets or quanta, resolved that snag. And his work laid down the foundation for everything that followed in quantum physics.
And it's so interesting that such a tiny constant, Planck's constant, plays such a huge role in the universe.
Very true. And while we're on the subject of constants, the speed of light, c, and the wavelengths corresponding to various types of electromagnetic radiation, radio, microwave, infrared, visible, ultraviolet, and so on, are all interwoven with these new ideas.
Yeah, and the equation, Cia-Belen, might seem simple, but it ties together the properties of light in a very elegant way.
Now, here's a point I find intriguing. The interplay between the wave and particle natures of light and electrons.
Oh yes, that dual behavior can be philosophically mind-bending.
Absolutely. It's an elegant, albeit sometimes frustrating, duality. You have phenomena that clearly show diffraction and interference, clean wave behavior. But then you have things like the photoelectric effect that
It's like trying to decide if you're at a rock concert
behavior.
or a symphony orchestra. Sometimes you get both.
Laughs, exactly. And when we talk about electrons behaving like waves, de Broglie's relation, where the wavelength is hmv,
Right?
really
And
highlights
his predictions were
this duality.
confirmed when electron diffraction patterns were observed. It's all interconnected.
Now, if I may, I'd like to respectfully challenge one common perception, Some say that because Bohr's model was so limited, it wasn't that important.
I'd actually argue it was monumental. Without it, the full quantum mechanical model might have taken even longer to develop.
I agree wholeheartedly. Bohr's model was a critical stepping stone. It bridged the gap from classical to quantum physics by introducing quantized orbits, even if it couldn't handle the complexity of multi-electron atoms.
Every scientist builds on previous work, and Bohr's insights paved the way for Schrödinger, Heisenberg, and others.
Exactly. And that narrative of continuously refining our picture of the atom mirrors how chemistry itself explains the vast diversity of chemical behavior. The electron configurations, orbital shapes, and reactive properties all stem from these early quantum ideas.
Yes, and it's what ultimately gives each element its unique fingerprint.
It's fascinating how a few core experiments and theories can lead us from a simple sigil of atom, meaning uncuttable, to our modern nuanced understanding of matter
Absolutely.
and energy.
It's like peeling back layers of an onion, each layer revealing deeper complexity.
If we measure an electron's position very precisely, its velocity becomes extremely uncertain.
Right, and vice versa. If we pin down its velocity, then its position becomes fuzzy, like trying to measure the thickness of a sheet of paper with an unmarked ruler.
Yeah, exactly. So this leads us to the idea that our measurements always give a blurry picture for these tiny objects, and that's exactly the heart of the Heisenberg uncertainty principle.
And the example with the meter stick, it's like using the wrong tool for the job, isn't it? I mean, trying to find the exact spot of an electron with, well, a tool that isn't fine enough.
Absolutely. It's like needing a super precise instrument, one that's calibrated way smaller than the electron size. Now moving on, this principle essentially demolishes the classical idea of a defined path or trajectory for electrons.
Yes, because if you can't know both position and momentum exactly, you can't really talk about an electron's path.
Exactly, and that's why Bohr's model, which obviously assumed fixed orbits like planets around a sun, just doesn't fit the quantum reality.
I agree, but let's be clear. Bohr's model made some sense for hydrogen, but it collapses under multi-electron scenarios, right?
Certainly. It really ignores the dual-wave particle nature of electrons. I mean, think about it. Electrons are described by these wave functions, PES, that give us probability densities.
Yeah, it's wild, like looking at a cloud of electron probability.
Right, and speaking of clouds, that brings us to the quantum mechanical model of the atom. It's all built on Schrödinger's equation, which essentially tells us where electrons are likely to be found, although it gives no fixed paths at all.
Absolutely.
And you know what's really fascinating? The Schrödinger equation gives us these quantized energy levels. In hydrogen, for example, 1s is the most stable. And then we get the excited states like 2s and 2p that are degenerate.
Right. But for multi-electron atoms,
energy.
Things get even more complicated.
In multi-electron atoms, the energy now depends not just on the principal quantum number, n, but also on the azimuthal quantum number, L, because of inter-electron repulsions and things like shielding.
Exactly. And that's why the filling order of orbitals is not as straightforward as it once was thought.
Now, let's break down these quantum numbers a bit. So, n defines the orbital's shell, basically its size and energy, increasing with distance from the nucleus. Yup. And then L tells us about the shape of the orbital. For instance, L-0 gives us s orbitals, which are spherical. And then L-1 means p orbitals, with their characteristic dumbbell shapes. And don't forget, each orbital gets further defined by the magnetic quantum number, ml, which tells you its orientation in space. And finally, ms, the spin quantum number, explains that tiny intrinsic spin, either +1,2 or 1,2, sort of like our electron's little internal compass.
Exactly, you can't have two electrons with the same set of these quantum numbers, as expressed by the Pauli exclusion principle.
And think about Hund's rule too. It tells us that electrons fill orbitals singly first to maximize their overall stability, thanks to exchange energy.
I've always found that bit intriguing. The idea that electrons prefer to stay unpaired until forced to pair up.
Right? Like they're being selective about sharing. It's almost like each electron has its own personal space, and they only come together when absolutely necessary.
True, though I sometimes wonder, don't you think this rule might be challenged by some exceptions? After all, nature often defies our neat categories.
Oh, for sure. There are exceptions. Chromium and copper are prime examples where the electron configurations depart from what we'd expect. But those exceptions actually highlight extra stability from having half-filled or fully filled subshells.
Exactly, and that extra stability is due to their symmetric electron distribution and exchange energy benefits.
Now, when it comes to orbital shapes, the s orbitals being spherical, p orbitals having those two lobes, and then d orbitals with even more complex shapes, it really demonstrates how quantum mechanics gives a visual, albeit probabilistic, picture of where electrons might be.
And these shapes also influence chemical properties, don't they?
Definitely. The electron cloud diagrams, which show regions of high probability from Bohr start to, help chemists understand why certain atoms form particular bonds and why molecules have certain shapes.
It's like nature's blueprint at the tiniest level.
Exactly. And then there's the Aufbau principle, the method of building up the electron configuration from the lowest energy level to the highest. The ordering is really like a staircase. Ones, then twos, then 2p, threes,
Yeah, the
and so
whole
on.
thing is like a very well-choreographed dance of electrons.
And the order is generally governed by the n plus L rule. The lower the sum, the lower the energy. If the sum is equal, the orbital with the lower n lies lower in energy. Right, though I've often wondered if the n plus L rule is a bit too simplistic for very complex atoms. That's a good point, but it definitely works pretty well as a guide for most elements. Moving on, when we talk about electron configurations, we also mention that core electrons are those in completely filled inner shells, while the valence electrons, which are in the highest energy level, are key players in chemical reactions.
Exactly. And that's why the periodic trends, reactivity, bond formation, and such, are so directly linked to these configurations.
Yep. And the beauty of it is that from the quantum realm to everyday chemistry, these principles create a coherent picture of atomic structure. I mean, it's like a symphony. Every quantum number and orbital plays its part to create the overall harmony. And the transition from the classical Bohr model, which is so clear-cut but fundamentally flawed, to this rich quantum mechanical perspective really shows how science evolves by challenging old paradigms.
Right, and it's a reminder that our understanding of nature is always a work in progress, improving with every discovery.
One could say that the quantum mechanical model isn't just an alternative. It's the truly more accurate picture. One that accounts for both the wave-like and particle-like
it's amazing to
nature
think
of
how
electrons.
these abstract concepts have direct implications in technology, like semiconductors and lasers.
Exactly. And it's also astonishing that the mathematical formulations behind these theories, like Schrödinger's equation, require a good dose of higher mathematics to crack. Yet they beautifully explain so much of what we observe.
It's a reminder of how intertwined math and physics truly are.
And speaking of deep exploration, when you look at orbitals, the idea of nodal surfaces comes into play. Those regions where the probability density drops to zero. It's phenomenal because it helps in visualizing the electron distribution.
Exactly, like one's orbitals are maximum at the nucleus and decay outward, but two's orbitals have that nodal pattern where they actually drop to zero before rising a bit again.
Right. And this nodal behavior is a key fingerprint that distinguishes one orbital from another, influencing properties like chemical bonding and reactivity.
Yes, seeing these probability diagrams really gives you an idea of the complex nature of electron behavior.
So, to wrap up, our discussion spans from Heisenberg's uncertainty through the blossoming of quantum mechanics via Schrödinger's equation, the quantum numbers that define every orbital, and finally to the filling of these orbitals guided by principles like Aufbau, Pauli, and Hund's rule.
Absolutely, it's a comprehensive journey from the microscopic principles to the macroscopic implications in chemistry.